In our next section, we're going to look at the IPv6 first hop security features, which we'll see are going to be fairly similar to what we have already talked about in IPv4 first hop security for the Catalyst switches in terms of things like DHCP snooping, IP source guard, and dynamic ARP inspection. And then we're going to be looking at their counterparts in IPv6, which are going to be referring to ICMP neighbor discovery. Now, before we get into the details of how the first hop security methods work and then how to implement them, one quick thing that I wanted to note about this is that most hardware platforms don't actually support these features yet. So if you want to practice this from a configuration point of view, you either need the newer switches like Catalyst 3560X or 3750X, or the ones beyond that like the Catalyst 3800 or 6509, 6800, and so on. So from a hardware point of view, the topology that I'm going to be using in this case for these examples is actually based on the ccie security topology. So if you are looking to actually test this out on the CLI, when you go to your members account, and if you go to ccie security and look at the rack rental guide for the particular topology that is used here, and then this would be under the basically just the introduction and then the hardware specification. So this particular set of rentals does have Catalyst 3750X running some of the newer code. And specifically here in the diagram, this is going to be switches 3 and 4 are 3750Xs, and then we have some routers attached to them that we can use to test out the end functionality for either being a client on the segment that is requesting an IPv6 address through stateless auto configuration, or the router that is actually generating the router advertisements. So if you try it out on your switches and you don't see the commands in there, then it means that you don't have the version of code that supports it. We'll see from a configuration point of view, the features are very straightforward. It's only a couple commands that you would need to run through. Most of it is really from a theory point of view to understand why do we need first hop security, and then what are some of the particular vulnerabilities that we can run into. Now, as the name implies, when we're talking about the first hop, we mean the access layer segment. So where we would normally be running the first hop redundancy protocols like HSRP, VRRP, GLBP. It's basically on the default gateway from the end host point of view. We're looking at this from the wired LAN point of view. Now, security mainly is going to be, in this scope, talking about preventing a man-in-the-middle attack or a denial-of-service attack that's happening on the access layer. Now, one thing that's kind of interesting we'll see here as it correlates to IPv6 first hop security is that there are some attack vectors that you don't need physical access to the access segment in order to actually implement. Where when we look at this in the case of IPv4, if someone was to do like a DHCP starvation attack or an ARP poisoning attack, they would already have to be plugged into that access segment. But in the case of IPv6, there's essentially a starvation attack that can be implemented even if you're not local to that link. So you can send packets to remote segments and then accomplish some of these particular attacks. Now, additionally, before we get into the nitty-gritty details, there's a resource that I would recommend that you guys take a look at, which is on the Cisco Live website. There's a presentation that is specifically about IPv6, or actually there's a couple of them. If you search IPv6 security, that is IPv6 security threats and mitigation, and then I believe there is another one that is just about first hop security, which is this one, Advanced IPv6 Security, Securing Link Operations at the First Hop. So this one, BRK Sec 2003, and then 3003. This would be a good place to look if you're wanting more additional resources after this particular section that we're going through. Now, the reason why we need first hop security is both IPv4 and IPv6 suffer from inherent insecurities in the control plane. So we talked about it previously in IPv4. When I send out an ARP request on the segment and someone replies back to me, I have no way to know, is that really legitimately the destination that I'm trying to reach? So one of the common attacks that we saw is that a new router or a new attacker essentially can come onto the segment and then poison the ARP cache by saying, I own the MAC address of the default gateway. which means that all the traffic would go to them before going to the legitimate destination. So if we were to think about this from a logical traffic flow point of view, essentially the way that the attack is implemented is that we have three devices on the LAN. We have the legitimate router, which is supposed to be the default gateway. We have the LAN segment, we have the victim, and then we have the attacker. So in this case, the attacker has physical access to the LAN segment. Now the victim, when it wants to do a resolution, so it wants to send a packet out to the rest of the routed network, it needs to resolve what's the link layer address, what's the MAC address that I use to forward traffic to the default gateway. So assuming that the victim knows that the default gateway's address is .1, and then it's basically sending an ARP request saying who owns .1 and what is the MAC address that it maps to. Normally, under legitimate circumstances, the router is going to reply with the ARP reply and say .1 equals whatever my MAC address, for example, A. Now, once the victim knows that the correct binding from the IP address to the MAC address, there's nothing to say that someone else in the segment cannot send a gratuitous ARP or an unsolicited reply that says .1 is not A, .1 is B, which would be the attacker's address. And then the ultimate result of this type of attack vector is that if the victim thinks the default gateway is over here, the traffic gets switched that direction, the attacker can rewrite it to the correct MAC address and then forward the traffic onto the final destination. So what's interesting about this is that it's a very difficult attack to detect, because when you generally look at the speeds of the LAN versus the WAN speeds, like if you go to web browse to your bank, for example, generally the bottleneck is not the LAN segment. So if you're rewriting the frames at gig-e speed, it's very unlikely that the end host is going to notice that the traffic is even being captured to begin with. So you would have to look at the low-level packet flow and then realize, hey, I'm forwarding to my default gateway and it's not using their particular MAC address. So there are, of course, ways to prevent it, which is what we're going to talk about here. But this type of attack is inherent both to IPv4 and to IPv6. So in the case of IPv4, we talked about what are some of their vulnerabilities. They are in address resolution protocol, and they're also in DHCP. Where in the case of a DHCP vector for this attack, I send out a discover, the attacker replies with an offer, and they use their address as the default gateway, which the same result is that the traffic is going to flow through them before it goes to the final destination. Now, in terms of IPv6, we have the same equivalence of these protocols, where we have ICMP neighbor discovery as opposed to address resolution protocol. And as part of neighbor discovery, we go through duplicate address detection. And we go through stateless auto configuration in order to try to get an IP address similar to DHCP. And then we use ipv6 for additional options, like our DNS server, for example. So another vector for this would be that I send out a DHCP request. The attacker replies back with a name server that is illegitimate. Then I go to resolve www.bank.com, and it goes to some phishing site as opposed to the legitimate destination. So ultimately, the end result of the attack is the same. It's just that on the LAN segment, there's multiple vectors in the control plane protocols that the attack can be implemented on. So it doesn't really make sense to secure one of them, like to secure IPv4 ARP, and then not secure ICMP neighbor discovery for IPv6 or DHCP or stateless auto configuration on its own. Now, as we talked about previously, from a control plane workflow, how does neighbor discovery work differently in IPv6 versus IPv4's ARP? In IPv4, it's a very simple protocol. We basically just have two messages. One is the request to say, I'm trying to resolve the mapping between the IP address and the MAC address. And then we have the reply saying this is the result that you're looking for. Now, in the case of IPv6, we have four messages. We have the neighbor solicitation, which is an ARP request essentially for someone who is not a router. Then we have the router solicitation that is like an ARP request but for the default gateway. Then likewise, we have two different responses. We have the neighbor advertisement. That's going to be the equivalent of the ARP reply. And then the router advertisement, which is the equivalent of an ARP reply, but from the router itself. Now, when an IPv6 host actually joins the LAN and it wants to start to send traffic, we talked about what's the specific process that it goes through. The first thing is that it needs to generate a link local address, in order to talk in the control plane to the other devices on the LAN. Like in order to get an address through stateless auto configuration, I need to be listening for that traffic to begin with, and the way that I'm going to listen is by running link local communication. So the end host is going to choose a link local address starting with FE80, and then normally it's going to generate its own identifier based on the MAC address, based on the EUI64 address. Now there are some other variations to this, like we talked about for a security point of view, that the end host may generate a random identifier so that we would not be able to correlate the mapping between the public routed traffic versus the MAC address of the end host. So either way, whether we're using EUI64 or not, the point is that we're generating the link local address, and then once we generate it, then we need to see if it is a unique address. So the way that we do this is by sending a neighbor solicitation for that particular destination, and specifically it's encoded as the solicited node multicast, it's called. But one of the issues about this is that if someone replies to the neighbor solicitation and it says your address is not unique, then the IPv6 host would not be able to join the network. So from a security point of view, one of the potential issues with this is that I could do a very low-level denial of service attack on you. You're trying to join the network and run IPv6. The only thing I need to do is listen for the solicited no multicast and then constantly reply back to you saying, no, your address is not unique. So beyond in IPv4, where we're doing just the regular ARP request and reply, this is an additional vector that could potentially be an attack with IPv6. Now, normally, assuming that no one replies back to us saying that the address is not unique, then we're going to announce ourselves as a live host. So we send to the all host multicast, FFO2::1, saying I own this particular IP address. In this case, it's link local, and then what the particular MAC address is that's associated with it. Now, once we actually have a link local address, then we can talk to the routers. So we need to discover the routers. We're going to send a router solicitation, and that's going to go to the all routers address, which is FFO2::2. Now, assuming that there's only legitimate routers on the segment, they should then reply back with the router advertisement that's going to give them information about what's the default gateway, and then what's the prefix that you would use for stateless auto configuration. Now, in the case that someone wanted to attack this, the only thing that we need to do is listen for router solicitations and then advertise back the wrong information. So advertise the wrong MAC address, advertise a different prefix through stateless auto configuration, maybe something that's not actually routable, and then the end result would be either a denial of service attack or it could be a man-in-the-middle attack. Okay, also, the same is true once we assign the address, the global address to the end host, then we have to go through duplicate address detection again. So this could be another potential way for denial of service, that I constantly reply back to you and say your address is not unique, and then you're not able to send any traffic onto the LAN segment. So if we think about what are the other potential ways that we could impact this, what are the other potential vectors for the attack? One way, like I mentioned, is that we could spoof the router. So instead of the legitimate router sending the router advertisements, I can send fake router advertisements with the wrong info, and it means that I would collect the traffic before it routes out to the rest of the network, or I could use that just for a basic denial of service. Another way would be to spoof the DHCP server. So I give you a wrong offer. The offer could have the wrong DNS server, for example, and then either your traffic gets routed through me or it just gets denied. We could also poison the neighbor discovery cache. So I can continue to send neighbor advertisements, which again are like our gratuitous ARPs or our unsolicited replies that has the wrong information. So if I want to knock somebody off the segment, the only thing I need to know is what is their IP address, and then I can send a neighbor advertisement with the wrong MAC address. So either to me or to some address that doesn't exist, and we wouldn't be able to switch that traffic. Now, one thing that's also interesting about ways that you can attack this is that this last one here can be accomplished even when you are not local on the segment. Now, when we think about in IPv4, the vast majority of times your end LAN segments are like a /24, which means you have somewhere around 255 hosts, give or take. So it's not really a huge amount of prefixes. It's not like a /8 where we have 24 potential bits for end hosts. There's only going to be 8 possible bits normally in most cases in most designs in the lab. But when we look at IPv6, the end segment based on the RFC is required to be a /64. So if we're to think about that just from a numbers point of view of how many addresses does /64 actually mean, it's some insanely huge amount. If you take 2 to the 64, you can see this is the number of end hosts that can be on that particular LAN segment. So one of the things that you could do would be to scan the segment with packets, which means that when the router goes to figure out, can I actually send packets to this destination, it's going to have to send a neighbor solicitation. So simply by doing just a walk of the addresses, just a basic IP scan, it's going to cause the router's neighbor discovery cache to overflow. Now the entries will be incomplete because assuming that end hosts don't actually own those addresses, but the router still has to allocate some buffers or some memory in order to do the resolution. So we're either essentially doing a denial of service against the CPU or doing a denial of service against the memory just by scanning the range of addresses. Okay, so we know some of the potential ways that we can implement the attack. Now let's talk about what are the different tools that we have that we can prevent the attack. So the first of which is going to be the IPv6 router advertisement guard. So essentially what this is going to do is for the layer 2 switch in the middle, it's going to figure out who is the legitimate router on the segment. So we can simply say from a port level point of view that I have my upstream interface facing towards the routers, and then I have my downstream interfaces towards the end hosts. Now, simply based on the fact that the end hosts are not routers, it means that I should not be receiving router advertisements in those particular links. So either by doing just a basic filter or by doing inspection of the actual neighbor discovery messages, the switch should be able to know which is an upstream link and which is a downstream link. So not only is it going to prevent someone from spoofing the router's address on the segment, we can also look inside of the payload to make sure that we're not trying to send router advertisements for prefixes with stateless auto configuration. Now, from a configuration point of view, the policy is going to be applied either globally to the VLAN or at the port level. The big thing to remember about this, and the same is true when we're talking about IPv4, like DHCP snooping, is that you need to make sure that the link that goes to the router is configured as a trusted port. Otherwise, the switch is going to deny the router advertisements coming in from the legitimate sources. So before we configure this on the CLI, let's take a look at where this is located in the documentation, because it is actually not very straightforward where you need to define these particular topics. So if we start at the main documentation page, we're going to go to products, iOS. Actually, no, not iOS. We're going to go to switches. Products and switches, then LAN access switches, 3750X, then configuration guides, and then our particular release. So this is going to be under and it may not be in this section. Not all of these versions, for some reason, have the document actually listed there. So you have to kind of do some digging to figure out which releases actually have it on there. We can actually go backwards as well through the, let's go to the routers documentation. Let's say iOS, regular iOS. Let's try 15S. Then IPv6 and IPv6 first hop security. Now, depending on, and this is kind of an odd release because the feature is for the Catalyst switches, but it's documented under the release for XE because the newer switches run iOS XE, like the Catalyst 3800, for example. So it is somewhere under the 3750X. If you go through those different releases, you'll eventually find it in there somewhere, but it should be the same for what's documented here under the regular iOS releases. So we have the router advertisement guard, IPv6 snooping, DHCP-v6 guard, and then IPv6 source guard. Now, you can think of these as very closely correlatable or very closely related to the IPv4 counterparts, where in IPv4 we had DHCP snooping, which of course is going to be DHCP-v6 snooping. We have dynamic ARP inspection in IPv4, which is going to be both the router advertisement guard and IPv6 snooping. And then we have the actual port level filter, which is IP source guard in IPv4, and then of course that's going to be IPv6 source guard for IPv6. So the first one we have here, which again is the router advertisement guard. The way that you configure this though is a little bit different than what we saw in the IPv4 counterparts. So the way that we do this is, first off, in global config, you need to configure a router advertisement guard policy. And the main thing that this is going to define, you'll see that there are other sub-options here, but the main thing that you really care about here is whether this is a trusted port or not. So the link that goes up to the router is the one that we need to put this flag on, the trusted port. So if we were to say that we had router 1 and then our end host, let's say the end hosts are A and B, and we're on VLAN 100, if we configure the policy globally and apply it to VLAN 100 and don't trust the link to the router, when the router sends the router advertisement, it's simply going to get denied. And you can see this when you configure it on the CLI. If we were to configure a very basic policy and then look at the debugs on the switch, you can see that it's filtering out the packets as they come in. So in our particular case here, if we look at the show CDP neighbors on the switch, we have routers 4, 5, and 6 that are connected on ports 1, 2, and 3. Then we have a link to another switch that's connected over a trunk link, which is on gig 1.0.22. So from a physical wiring point of view, let's assume that router 6 is our default gateway. We would need to say that the port that goes to, so this would be, this is us, this is switch 3 in the middle. So that particular port, gig 103, we would need to say that this is the trusted port. And then as we go down to the other end hosts, as we go to router 4 and we go to router 5, these would be the ones that we're applying the inspection policy on. But then as we go to the trunk link to the other switch, those links would also have to be trusted, because we're normally assuming that behind the other switches, there's probably some routers there that are sending the router advertisements. So it's a little bit easier to make a mistake in the config and filter out the legitimate messages versus the IPv4 counterparts. So globally on switch 3, we're just going to say IPv6, neighbor discovery, router advertisement guard, and we're going to configure a policy. Okay, we'll say that the policy is for our untrusted links. And under here, basically, we're going to say that the role is going to be an end host. So this is actually by default that when you configure the policy is for untrusted neighbors, and the device role is going to be the end host. So essentially what it's doing here is saying when I'm doing snooping in the data plane and I'm looking in the actual payload of the neighbor discovery messages, should I be receiving the router advertisements, so the actual ICMP NDRAs, those would come from the router. Or if I was attached to another switch, there might be multiple advertisements coming in. So this is the way that the switch is categorizing, is the port upstream or is the port downstream. Okay, we could also say what's the number of hops that are advertised. This would be for preventing basically like a remotely implemented attack. Do we want the manage config flag on? This would be whether you are using your DHCP v6 server or not. And then the other config flag is going to say specifically where is the DHCP server. So if you're running both at the same time, if you're doing stateless autoconfig and you're doing DHCP, then you would set these flags to say, yes, the router should be advertising those, or no, the router should not be advertising those because we're not implementing DHCP v6. Either we are implementing it or we're not. Okay, then you can look also inside of the payload of the neighbor discovery message to match against what is the actual prefix that should be advertised for stateless autoconfig. So if we know that on this segment the subnet is supposed to be 2001::/64, we can configure an ACL to say this is what the router should be advertising exactly. And if you see anything else, it means that someone else is trying to spoof the payload. But at a minimum, basically, we don't even really need to do anything because for untrusted ports, the default role is host and trusted port is off. Okay, the other role would be if we were to say this is going to be trusted. So the device role would be the router, and we're going to say that this is going to be on the trusted port. Now, when we actually go to apply this, we can apply it either at the interface level or we can apply it globally. So at the link level, we would say IPv6 neighbor discovery router advertisement guard. What's the policy name? And then what particular VLANs does it actually apply to? By default, this is going to be all. So, and if you're configuring this on a trunk link, you have multiple VLANs that exist on the trunk, then it's going to enforce it for all of them. So if you have some segments that you don't want to do the snooping on, then you would just exclude it from the particular port level. Okay, so we're going to say here that specifically if we look at our physical wiring again, we have router 6 connected to switch 3. And then we have router 4 and router 5. And these are on ports gig 101, 102, and 103. So on the router side, we're assuming that at the link level, this is F00, I believe, that we're running IPv6. Okay, so we have IPv6 enabled, and let's actually say that this is going to be the router. So on this link, we're going to say, first off, globally, IPv6 unicast routing. Then at the link level, IPv6 address, we'll give it a global address. And since we have IPv6 routing on globally, it means that as soon as we enable an address at the link level, we're going to start to send router advertisements with our global unicast address for stateless auto configuration. So now if we were to go to router 4 and router 5 and tell them to get an address through stateless auto config, we should see that they're going to automatically learn that particular prefix, 2001::/64. So on router 4, if we look at our config here, let's say we don't have an address, and also we're not running unicast routing globally. No IPv6 unicast routing. At the port level, we're just going to say IPv6 address is through autoconfig. Okay, if we then look at the show IPv6 interface brief, we should see here shortly that we're going to learn our address through autoconfig. Now on the switch, we're getting a log message that says we dropped a message on gig 103, and the reason is that the packet is not authorized on the port. Okay, specifically the packet it's talking about is the neighbor discovery router advertisement. So in other words, right now the link is configured as untrusted, so we're filtering out the advertisement. Normally, this is what you would want from your downstream facing links. So whatever is going to the end host, they should not be generating router advertisements because they're not the legitimate default gateway. So if we look at what we have configured on the port level, I had previously configured this with the untrusted policy. So you need to make sure that whatever link that goes to the router is going to be the trusted policy. And actually that should be, let's say show run section IPv6. That actually would not be the snooping policy, that would be the, well, I do have the snooping policy configured. They're technically two different features, but you would normally run them together. Where the router advertisement guard is just going to be just for the RA messages, IPv6 snooping is going to be for creating the IP address and the MAC address bindings. So normally you run all of these features together, which DHCP guard, just like we had on IPv6, or excuse me, in IPv4, we had DHCP snooping. In IPv6, we have DHCP-v6. So we would use this to make sure that that we're not we're not learning the wrong default router through router advertisements, or in the case of we're running DHCP-v6, that we would prevent spoofing of the server, so that someone's not advertising the wrong DNS information, or they're not advertising the wrong prefix for stateless auto configuration, or actually that would be non-stateless config if we're running DHCP. But like in the router advertisement guard, we can apply it either at the port level or the VLAN level. Now, when we look at the actual payload, that's what IPv6 snooping is doing. So it's similar in behavior to IPv4 dynamic ARP inspection, that not only are we looking at what type of message are we receiving, so are we receiving a router advertisement or are we receiving a neighbor advertisement, we're looking into the payload to look at what the actual values are. So based on either the DHCP messages or neighbor discovery, we're going to create a binding table, where the binding table is then going to have an association between what was the end host's IP address and what was the end host's MAC address. Once we know the legitimate association, we can then use this to secure not only the control plane, so to make sure that someone's not advertising an address they don't own, but also to do filters in the data plane so that when packets come inbound, we can make sure that they match against the correct IP address and the correct MAC address. Now, the other thing to think about here, just as in IPv4, if you have devices that are not doing auto-config, you need to make sure that they have manual bindings. Like in the case of IPv4, if you're doing DHCP snooping and you have devices on the LAN that aren't running DHCP, like maybe you have printers or the router or some other device, like maybe like a wireless access point, that if the switch doesn't know what the correct IP address to binding, MAC address binding is, then it's going to drop those packets in the data plane. So same type of logic as IPv4, where we would do a manual binding, and then like the other features, you could apply this either at the VLAN level or you could apply it at the port level. Okay, then we have IPv6 source guard, which is similar to IPv4 source guard, which is going to use that snooping table in order to actually affect this in the data plane. So essentially what it's going to do is automatically create an ACL that says this is the IP address, this is the MAC address, and that's applied to ingress on the interface. So from a configuration point of view, technically they're unrelated features. The router advertisement guard, the snooping DHCP guard, and IP source guard, but in reality you would configure all four of them at the same time. So in our particular case here, we had IPv6 snooping on, which was saying that there was an untrusted policy, and then the end result is that the router advertisement comes in and it says, I'm going to drop this because it's not authorized on the port. So if we look here specifically at the link level, we're going to have a policy now that says we're trusting that, and for IPv6 snooping, but also for neighbor discovery, router advertisement guard. So we're going to attach the policy that is trust. So they're named the same thing here. Probably you would name them separately so you can keep track of one versus the other. So this policy here is technically unrelated to this one. They just happen to have the same names. Okay, now if we were to look at debug IPv6 neighbor discovery and debug IPv6 snooping, this should show the actual packet exchange. So on the router here, if we were to say no IPv6 address, and let's give it a new address, IPv6 address 2001:1:6. So it's on a different subnet. We should see the advertisement come in, and it tells you specifically what was in the payload. So here we can see duplicate address detection is not being filtered. The message is allowed through. Then we should see that there's a router advertisement come in, which you can see it's kind of a noisy debug, but somewhere in here it should say what's in the payload for the router advertisement. So router advertisement was received, router advertisement guard is running, but the end result is that the link is a trusted port, so the end result is that we're going to allow it through. Now if we were to go to the other devices, like router 4, for example, and we look at show IPv6 interface brief, we can see now we were actually allocated an address, and again, this is coming from stateless auto configuration. So the only thing router 4 is doing here from a configuration point of view is just to turn IPv6 on. So we're saying get an address through autoconfig. From the router's point of view, from router 6, it's simply enabled IPv6 unicast routing globally, and then we have the address configured on the interface. So by default, we are always going to send router advertisements as long as routing is on. And as we talked about previously in IPv6, you can turn this off if you wanted to for some reason. So you could say IPv6 neighbor discovery to router advertisement suppress. Okay, that would turn it off, but the default value of this command is no IPv6 neighbor discovery router advertisement suppress. So once we actually learn about these bindings, if we show IPv6 snooping, and we should see say neighbor discovery inspection. So let's see, how do we check the actual database? This should be under IPv6 snooping. Verifying and troubleshooting inspection. Displays the policy, display the counters. Neighbor binding, that's what it is. So this we can see now that the switch is learning on those particular ports, what are the end hosts, and then what are the addresses that they are specifically allocated. So assuming that we were to turn on a source guard on the link, and then if we were to change the global unicast address that the routers have assigned, then it would start to drop the packets in the data plane. But again, just like we saw in IPv4, the issue we would run into is that if the switch cannot learn this information, then it is going to drop packets, it's going to drop any packets that come inbound. So it has to know on the particular port what's the association from the IP address to the MAC address. And the issue that when we would run into that issue is if you're doing static addressing. And now in the case of IPv6, you very rarely do static addressing. Normally it's only on the router, and everyone else is going to be running autoconfig and just getting the stateless addresses from the routers. But if for some reason you do have devices that are statically numbered, then you would have to do the manual bindings for them. So it's similar to like we talked about in IPv4. This is going to be here under IPv snooping, and then configuring the binding table. So we would say that there's a neighbor in VM100. This is the IP address that they own, and then they're on that particular link. And then in here somewhere, there would also be you could also bind it directly to their MAC address as well. Now, beyond these features, there's another implementation that is designed to fix the problem in the control plane directly, and not to fix it by doing these inspections and these filters on the layer 2 switches in the middle. Because as you can imagine, and most switches currently don't support the feature, so there's no way to do the inspection, or there's no way to do the port filters. So another option is to offload this directly to the client and to have them know what the legitimate router is on the segment. And specifically, that implementation is called Secure Neighbor Discovery, or SEND. So this is an extension onto the end host to say that we're going to run public key infrastructure, or PKI, so that we would trust a certificate that is allocated to the legitimate router on the segment. Now, the end hosts themselves don't need to get a certificate, so you don't have to generate them for all of your phones, all of your laptops, and so on. We only need to have one certificate for the router, and then the actual end host, like Windows, Mac OS, would have to trust the router's certificate. So then the end result is that the router advertisements and the solicitations are essentially authenticated between the router and the end host. Now, from a configuration point of view on the router, as you can imagine, this is much more involved. The reason why is that we need PKI. So I would assume that within our particular scope for ccie RNS, that Secure Neighbor Discovery is not going to be tested on, because this would be going way above and beyond in order to do the actual PKI implementation, to configure the certificate server, to do the enrollment, to actually get the cert, and then install it for the purpose of neighbor discovery. This is going to be something that's reserved mainly for the security exam. So you may want to read about it. It's an interesting implementation, and you would probably want to run this in a real design if you could, because then you don't need to do snooping, source guard, DHCP snooping, router advertisement guard on the switches in the middle. You're basically solving the problem natively by pushing it off to the application.